All right, here goes. Some basics about probability, some definitions, terminology that I want to make sure you're comfortable with. First of all, the sample space. The sample space for any event is just all the possible outcomes. So let's just say we were going to roll a single six-sided die, just one single six-sided die. We could list out the sample space because there are really just six things that could possibly happen. 1, 2, 3, 4, 5, or 6. That would be it. That would be all of the possible outcomes for rolling a single six-sided die. And anytime we use the term sample space, what we're talking about is all the things that could possibly happen. That's the sample space. Two different types of probability. One's going to be way more important for us than the other, but I want to make sure you're familiar with both. The first of those is theoretical probability. This is what should happen. We calculate this. If we flip a coin a bunch of times, we expect half of those to come up heads, half of those to come up tails. This is what should happen. And oftentimes, the probabilities we work on are going to be theoretical in nature. We're not actually going to flip the coins. We're going to use the probability of that item or items to calculate the theoretical probability. And this is the type of probability we are primarily going to work on. But I do want you to be aware of the other type of probability that is experimental probability. Experimental probability is the result of an experiment or an activity. So instead of saying, well, probability says if you flip a coin 1,000 times, you should get 500 heads, 500 tails. Experimental probability is actually flipping the coin 1,000 times and writing it down, actually doing the activity. Now, for our purposes, theoretical probability is going to be most of the time, but experimental probability is valuable. For example, an activity I've done before is if you have a thumbtack and you flip it, what's the probability it's going to point straight up? I have no idea what that would be. So really the only way to answer that question would be to actually perform the experiment, do the activity, and see what the probability turns out to be. So experimental probability is very useful. It's just for the most part, we're going to work on theoretical probability. Some other words for experimental probability that you might see, it's also known as relative frequency or empirical probability. All of those terms, experimental, empirical, relative frequency, they all mean the same thing when you're actually doing an experiment. Probabilities we work on will mostly be theoretical in nature. The most important thing about probability, this is the thing I'm going to say over and over and over again today, and probably even into next week a little bit, but probability is equal to successes over outcomes. Probability is successes over outcomes. No matter what kind of probability question you're working on, what you're looking for is how many outcomes are there, how many successes are there, and then we're going to write that as a probability. Sometimes as a fraction, sometimes we'll take it one step further and write it as a decimal, but the main idea is probability is successes over outcomes. I do want to make one little note about this word right here, successes. This doesn't necessarily mean winning or something good. It just means, did the thing that I was looking for happen? If so, that's a success. Doesn't necessarily mean winning, doesn't necessarily mean anything good. But this right here is the most important thing about probability. Some probability examples. If we are supposed to find the probability of an event, for example, a single six-sided die is rolled, find, and this notation over here with the P and the thing in parentheses, that means find the probability of this thing happening. So that's what that notation means there. P of 3 means find the probability of getting a 3. So a single six-sided die is rolled. Find the probability of getting a 3. And we looked at the sample space for a single six-sided die earlier. It was just 1, 2, 3, 4, 5, 6. That's it. That's everything that could possibly happen. Keeping in mind that probability is equal to successes over outcomes, if we want to find the probability of getting a 3, then what we need to do is write this as successes over outcomes. I can look up here and see that there are 6 outcomes. 1, 2, 3, 4, 5, 6. There are 6 different things that could possibly happen. So there are 6 outcomes. The number of successes. Remember, success doesn't mean something good. It just means how many ways can this happen? How many ways can I get a 3 on this single six-sided dice? How many of these outcomes are a 3? And don't overthink it. It's exactly what you're thinking. One way. You're exactly right, Kevin. There's one way for me to get a 3 on there. So I have 1 success. I have 6 outcomes. So the probability of rolling a 3 is 1/6. We're going to write probabilities as either fractions or decimals. A lot of times as fractions. We're going to kind of focus on the fractions for the most part today. Oh, good, Arian. I just saw yours come in there too. So probability of rolling a 3 is 1/6. Probability of getting an odd number. Well, probability of successes over outcomes. So I still have 6 outcomes. And now I want to look for my successes. How many successes are there? Well, that's an odd number. 2 is not. 3 is an odd number. 4 is not. 5 is an odd number. So I have 3 different ways to have a success here. The 1, the 3, and the 5. So I have 3 successes, 6 outcomes. So the probability of getting an odd number is 3/6. A really good question that you might ask is, do we have to reduce that to 1/2? And my answer is no, you don't. You can if you want to. If you wanted to reduce that and have your answer be 1/2, you absolutely can. But you don't have to. And there's a reason for that. You may have had an elementary school teacher somewhere along the line that, or somebody that you taught you fractions and said, anytime you can reduce, you better reduce. I don't think that's a bad policy in general. But with probability, there's a reason, there's some value in not reducing. And what it is this. While these 2 probabilities are equal to each other, both are correct answers. This one actually tells me how many successes there are and how many outcomes there are. And this one doesn't do that. They're both correct, but because the unreduced fraction lets me know how many successes and how many outcomes there are, it's going to be perfectly fine for you to not reduce fractions in questions that are about probability. So for all the probability questions we do, if you get 3/6 as an answer and want to leave it as 3/6, that is just fine. Any questions on those before we look at a couple more? Okay. These might seem silly at first, but hang in there with me. I promise there is a method to my madness. A single six-sided die is rolled. Find the probability of getting a number that is less than 15. Well, we saw the sample space. It's 1, 2, 3, 4, 5, 6. So if that's my entire sample space, the probability of getting a number that's less than 15, keeping in mind the most important thing about probability is that it is successes over outcomes. Well, I have 6 outcomes here, that's for sure. And a number less than 15, well, they're all less than 15, all 6 of them. So I have 6 successes and 6 outcomes. So the probability of getting a number less than 15 is 6 out of 6. If you're thinking, well, that seems pretty obvious, I don't see where you're going yet, hang in there, I promise. Probability of getting a 15. Okay, well, 6 outcomes. How many of these numbers are a 15? Well, none of them are. 0. The probability of me getting a 15 would be 0 out of 6. Hopefully those two answers make sense to you. If not, you let me know. The probability of getting a number less than 15 is 6 out of 6. The probability of me getting a 15 is 0 out of 6. Where this is going is this. Probability of getting a number less than 15. Well, this is going to happen every single time. This is always going to happen. Every time I roll that single six-sided dice, I'm going to get a number less than 15. That is always going to happen. And 6 out of 6, I could rewrite that as just 1. 6, if I divided it and made it as a decimal, it would be 1. And then if I look at the other one down here, I roll a single six-sided dice, I'm never going to get a 15. That's never going to happen. Something that's never going to happen, if I were to write this one as a decimal, would be 0. So let's put this together a little bit here. Something that always is going to happen every single time without fail has a probability of 1. Something that's never going to happen, no matter what, has a probability of 0. What this tells us is that all probabilities are between 0 and 1. Because something that will never, ever, ever happen, no matter what, never has a probability of 0. Something that will always happen every single time has a probability of 1. So all probabilities are between 0 and 1. Now, if you're thinking, well, it doesn't leave a whole lot of possibilities for answers, well, sure it does. Because remember, probability of success is over outcomes. So I could have an answer that looks like 1 out of 6 or 6 out of 6 or 13 out of 74 or 91 out of 200. There's an infinite number of fractions that could be my answer. It's just every one of those has to be between 0 and 1. How this helps you out is if you're working on a probability question and you get to the end and the answer you have is 17 over 4, that's bigger than 1, so it can't be correct. It's sort of a self-check that's built into here. Anytime you get an answer that's bigger than 1, if your numerator is bigger than your denominator, something's gone wrong somewhere because it has to be between 0 and 1. Any questions up to now before we kind of keep going on our probability questions? All right, we're going to ramp up the difficulty a little bit here, and we're going to look at rolling a pair of dice. Instead of just rolling one single individual die, now we're going to roll a pair of dice. And as you can see from this picture, there's a heck of a lot more outcomes with a pair of dice. What's going on here is related to the fundamental principle of counting from Tuesday. I've got a red die and a green die. When I roll the red one, there are 6 possible outcomes. When I roll the green one, there are 6 possible outcomes. Find the number of choices for each space, multiply those together, so there must be 36 total outcomes when I roll a pair of dice. And that's what we see in this chart right here. I've got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So this is a 6 by 6 array of all 36 possible outcomes. If you're thinking, wait a minute, when you roll a dice, the only thing you can get is between 2 and 12. Well, that's if we add them up. If we don't think about adding them up for a minute, if we just say, what are the different things that could happen? That's what this is a picture of. All the different things that can happen. There's a little bit of something I need to discuss that comes up with students sometimes in here. And it's the idea that a 1 with a 2 is written twice. So let's take a look at just those 2 outcomes briefly. So the one that's on the left of those is a red 1 and a green 2. And the one that's to the right is a red 2, a red 2 and a green 1. The reason those are different from each other is because what is on the dice has changed. It's not because we changed the position of them. If I were to just put the green 2 over here and the red 1 over here, now these two are the same as each other. I just moved them around the table. That doesn't change what the outcomes are. But because what is showing on the dice is different, those two outcomes are different from each other. So it's not about the position of the 1 and the 2 on the table. It's because here, the red dice is different from what it used to be, and so is the green dice. So that's why those are different outcomes. 1 on the red, 2 on the green is a different outcome than 2 on the red, 1 on the green. Often, the next question that goes through people's heads is, okay, well, how about that 3 and 3 right there? How come it's only in there once? How come it's not in there twice? That's an excellent question. If we have a 3 on the red and we have a 3 on the green, moving those around the table doesn't do anything. And if I change it to 3 on the red, 3 on the green, it's the same outcome. So the reason that that doesn't appear twice is because if I change what's on the dice, now I no longer have 3 with 3. If it's a 3 on the red and a 3 on the green, there's only one way for me to do that. And so that's why that's only listed one time. It's important for me to make sure you're comfortable with the idea that there are 36 outcomes, that 1 on the red, 2 on the green is different from 2 on the red, 1 on the green, and that 3, 3, 4, 4, 5, 5, 6, 6, these only occur one time because I can't change it and still have those numbers be on the dice. Let me know if you have any questions about that. If you don't, that's outstanding. Okay. Dice make for excellent probability questions. And so this is representative of the type of question you could see related to dice. We're going to roll a pair of dice. What's the probability that the sum of the faces is 10? So we roll a pair of dice. What's the probability the sum, what we get when we add them up, is 10? I'm going to go back to the other page so that you have that chart to look at to answer this question. What is the probability that the sum is equal to 10? I'm going to set up a poll for this one and give you a chance to try it. As you answer this question, and please answer this question, it'll give me information on how you're doing with the dice, how you're doing with this diagram, and most importantly, the most important thing about probability is successes over outcomes. If you're supposed to answer a probability question, what you're doing is how many outcomes are there, how many successes are there, and then you write that down as the probability. And so what we're looking for here is how many outcomes are there? That one should be pretty easy. And then how many successes are there? How many of those outcomes in that chart have a sum of 10? If I add the faces of the die together, I get 10. Because those are our successes. Keep in mind, I don't win anything. Nothing good happens if the sum is 10. It's just, that's what I'm looking for. So that's why we call those successes. I think this is a really useful diagram. And so it's in your book on page 303. I'll write that down once we finish up the poll. We'll go another 20 seconds and then talk through it together. All right, let's see where we are on this one. Okay, not unanimous, but some agreement. Not everybody's in on this one, so make sure you ask questions if you have them. Probability is successes over outcomes. So the first thing we know we're going to do is put our outcomes on the bottom. We know there's 36 of those, so we have 36 outcomes. Now we just have to identify our successes. Those successes are when the sum of the two faces is 10. So let's see, if I start down here, the sum of those is 12, so that's no good. Sum is 11, no. 6 plus 4 would make 10. 6 plus 3 is no good, so I don't need any more of the 6s. Let's see, 6 and 5 would be 11. 5 and 5 would make 10. 5 and 4 is 9. 5 and 3 is 8. 5 and 2, nope. 6 and 4 would, or 4 and 6 would make 10. 5 and 4 is 9. That's it. That's it. Those three right there. 6 with 4, 5 with 5, and 4 with 6. Those are the only ways that I can get a sum that's equal to 10. So on this whole picture, I have 3 successes out of 36 outcomes. So the probability of getting a sum equal to 10 is 3 out of 36. And that could be reduced to 1/12, but you don't have to. You can leave it as 3 out of 36. Are there any questions about that one before we look at another one together? Okay. 2 dice are rolled. So we know we're going back to that picture from page 303. What is the probability that the sum of the faces is less than 5? Less than is really important here because we want the sum to be less than 5. Not exactly 5, less than 5. So we could have a sum of 4, we could have a sum of 3, we could have a sum of 2. That's it, because there's no way to get a sum of 1 if I roll 2 dice. So I'm looking for sums that are 4, 3, and 2. Those are the ones that are less than 5. So if we go back to our diagram here, and what we're looking for now is the probability that the sum is less than 5. Most important thing about probability is successes over outcomes. We know we have 36 outcomes, so we know that much without really even using this picture. Sum is less than 5, so I need to find the places where the sum is less than 5. Well, that's less than 5. 1 plus 1 would be 2. 1 and 2, that's 3. That's less than 5. There's a 2 and a 1 over here. That's less than 5. 1 and 3 would be 4. 2 and 2 would be 4. 1 and 3 would be 3 and 1 would be 4. That counts. 4 and 1, that's 5. So my instinct is to count it, but wait a minute, it didn't say 5, it said less than 5, so that one is no good. Can't have that one. So what I end up with here is 1, 2, 3, 4, 5, 6 successes out of 36 outcomes. So the probability of getting a sum less than 5 is 6 out of 36. You could reduce it to 1/6, but you don't have to. One of the things I want to kind of point out about this picture, along with the fact that it's on page 303 in your book, is when you're looking for sums, just sort of the way this is drawn, it's really convenient. You see this, there's a diagonal line here that has sums of 10, and a diagonal line here, sums of 11, and then a diagonal line here that's sums of 9, sums of 2, sums of 3, sums of 4. So there's a pattern there that we can use to help make this picture even more useful than it already is. Does anybody have questions about what we did there to find the probability of rolling a sum less than 5? Fantastic. Very good. A couple of words that I want to talk about with you. And or. Daily conversation, these words kind of feel very similar to each other, and or, but the reality is they're extremely different from each other. And when we talk about probability questions, those differences are going to be really important for us. If we see the word and in a probability question, to have a success, both things must happen. So, and you'll see examples of these very soon, I promise. But if it's and, both things have to happen for it to be a success. In contrast to this, if it's or, to be a success, just at least one of the things must happen. Doesn't have to be both, just at least one has to happen. I do want to talk about the word or a little bit, and we'll kind of take a side trip into English class just for a minute. There's two different types of the word or. There's exclusive or and inclusive or. Exclusive or is what happens when you go to a restaurant and they say, do you want soup or salad? It would be nice to be able to say, bring them both. That's not how it works. You either get soup or you get salad. You can't have both. That's the exclusive part of this. You can't have both. You either get one or the other, not both. Inclusive or would be more like if you went up to a hot dog vendor and he said, do you want ketchup or mustard on your hot dog? In that case, it's perfectly fine to say, I'll have both. That's inclusive or, because you're allowed to have both. And inclusive or is the or that we use in mathematics. So it's inclusive or that we're using in mathematics. So when we say the word or in a problem, then at least one of the things must happen. It could be the first thing. It could be the second thing. It's also okay if it's both. And so that's why we say or is tied to you just need at least one. Could be more than one, but as long as you have at least one, it's a success. So we're going to take a look at problems that use the words and or. I want to make sure that you're comfortable with the difference between those two words. Let's take a look. We talked about dice. Dice make great probability questions. A deck of cards also makes for great probability questions. Some of you may be really comfortable with the composition of a deck of cards. Others maybe not so much. If you're very familiar with a deck of cards, I apologize a little for what's about to happen next. If you're not familiar with a deck of cards, this is what we're going to talk about for a few minutes, is how a deck of cards is constructed, what's in there anyway. The first thing that's important for us to take note of is that there are a total of 52 cards. So there's a total of 52 cards, and those cards are divided into 4 suits. And those suits, and you can see the picture on there, are hearts, diamonds, clubs. When kids are little, they often are told that those are puppy feet. And then the ones that look like shovels are spades. So we have hearts, diamonds, clubs, and spades. Each of those has the same number of cards in it. They each are made up of 13 cards. So there's 13 hearts, there's 13 diamonds, there's 13 clubs, and there's 13 spades. You can see by looking at the picture and from my writing that then there are 26 cards that are red, and there are 26 cards that are black. Within each suit, there are 13 cards, like I mentioned, and what you'll see there is ace, which is like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then we get to those last 3. Those last 3 there on the end have pictures of people on them, and the J is the jack, the Q is the queen, and the K is the king. So it's the jack, the queen, and the king. And that's how we get to our 13 cards. It's essentially 1 through 10, and then jack, queen, king. The Jack, Queen, and King, because they have pictures on them, are often referred to as face cards because they have faces on them. And that's sort of the makeup of the deck. That's the 52 cards that are in there. You can see this picture in your book on page 305. So if you need to refer back to that, you can. I wouldn't give you this picture or the other one, for that matter, of the dice during an exam. So you want to make sure you're comfortable with the deck of cards, comfortable with the makeup of a deck of cards. Yeah, problems involving a deck of cards. And this is where our and or questions are going to come in, but we start out relatively straightforward. One card is drawn from a standard deck. Find the probability of getting a 7. So simple as that. We have these 52 cards here total. We want the probability of getting a 7. Keeping in mind that probability is successes over outcomes. Well, let's see. One thing I do know for sure is I'm drawing one card from a standard deck, so I'm going to have 52 outcomes. My question for you is, how many 7s are in there? How many successes are there? And some of you may just know how many 7s are in the deck. Some of you may look at this picture and figure out how many 7s there are in a deck. How many 7s are there in the deck? 4. Perfect, Kevin. We can find our successes. There's 1, 2, 3, 4. I have those 4. The 7 of hearts, 7 of diamonds, 7 of clubs, 7 of spades. I have 4 successes out of 52 outcomes. So the probability of getting a 7 is 4 out of 52. You could reduce that to 2 out of 26 or 1 out of 13, but you don't have to. You can leave it as 4 out of 52. Again, really emphasizing that probability is successes over outcomes. We find out the probability of getting a 7 is 4 out of 52. Now we run into our and or questions. First one says, what is the probability of getting a 7 and a heart? Keep in mind, we're only picking one card. So I'm picking one card and I'm looking for the probability of getting a 7 and a heart. I know that there are 52 outcomes. So denominator, that's no problem. I need a card that is a 7 and a heart. And means it has to meet both of those conditions. So I go back and I look, and I'm looking for a card that is a 7 and a heart. Okay, this one is. There's no other cards up here. That's a 7, but it's not a heart. So that's okay. Okay, the only card in the whole deck that is a 7 and a heart is that one right there, the 7 of hearts. That's it. That's the only one. In order for and to have a success, both things have to happen. I have to get a card that's a 7, and I have to get a card that's a heart. I'm only picking one, so it has to be this one right here. So I only have one success out of 52 outcomes. So the probability of getting a 7 and a heart is 1 out of 52. Let me know if you have questions on that. I'm about to do that next one at the bottom there. The probability of getting a 7 or a heart. 7 or a heart. All right, well, I know there's 52 outcomes. There's one way to do this that I want to talk you out of. And that is to say, well, I know there's 4 7s in the deck, and I know there's 13 hearts in the deck. So if I add those together, there's 17 successes. So 17 out of 52. Seems reasonable. What's the problem with that? Because I'll go ahead and tell you that's no good. What's the problem with doing it that way? Excellent, Ashley. One of the 7s is already a heart. So what we're doing if we do that, if I say, well, there's 4 7s in the deck, so I'll count those. And then I'm going to count up all these hearts. So I counted the 4 7s, and now I'm counting the 13 hearts. And the problem is I counted the 7 of hearts twice, and that's no good. I don't want to count anything twice, so I've got to be a little bit careful with this. What I could do is say, okay, I'm going to count all 13 hearts, and then I'm going to count the other sevens to end up with 16 successes. You could also say, all right, I'm going to count up these 4 sevens, and then I'm going to count the other 12 hearts, and I still end up with 16 successes. Either way we count that, we end up with 16 successes out of 52 outcomes. So the probability of getting a 7 or a heart is 16 out of 52. I just want to take a pause for a second and note the significant difference between the words and or. These two problems are almost identical. If we cover up this word, they're exactly the same as each other. But if I want the probability of getting a 7 and a heart, it's 1 out of 52. If I want the probability of getting a 7 or a heart, it's 16 out of 52. Very different answers because and or have very different meanings. Let me know if you have any questions about that before we move on to another type of probability that we're going to look at today. Okay. This is a type that tends to go extremely well for students. I hope the same is true for you. Probability from a table. Data from a recent 5K run for charity were compiled, and we got this table. There were adults in this run, there were children. Some of the people ran and some of the people walked, and that's what we see here in this table. And our job is, if we were going to pick one person at random from everybody who participated, find the probability that a person chosen at random is an adult. So what we're after here is, I'm just going to pick one person at random, and I want the probability that that person is an adult. So what I'll need to do here then is, same as always, find successes over outcomes. The outcomes is, well, that's everybody I could possibly pick from. And so to get that, I'm going to have to add up all 4 of these numbers to get the total number of people who were involved. My total outcomes, 23 plus 11 plus 14 plus 22. I've got 70 outcomes. Successes, those would be the adults. So I need to go through here and identify the adults. They would be in this row right here, 23 and 14. So it looks like altogether there are 37 adults. So there are 70 total outcomes. 37 of those are adults. So the probability that I pick somebody at random and get an adult is 37 out of 70. Let me know if you have questions on that before I have you try one. Very good. Okay, here goes. Same idea. We have data from a 5K run. Some people ran, some people walked, some people were adults, some people were children. Find the probability that if we choose one person at random from this entire group of people, that that person walked when they did the 5K. So we're finding the probability that a person chosen at random was somebody who walked. I'll set up a poll for you and give you a chance to try this one. This is one that students tend to do really well on. I'm guessing the same will be true for you. We'll go another 30 seconds and then talk about it together. Let me know if you need more time. Let's see how we're doing on this one. Unanimous, outstanding. Kind of what I expected, but I'm glad it turned out that way. Let's go ahead and take a look at this one together just to make sure. If you have questions, you let me know. We want the probability that a person chosen at random was somebody who walked. And we know there are 70 total people, so that's our outcomes. And then we need the people that walked. There's 14 adults and 22 children, so that's 36 people altogether. So 36 out of 70 is the probability that we get somebody who walked. I mentioned earlier today that we're going to write probabilities as fractions and sometimes as decimals. If you're asked to write a probability as a decimal, and let's say it needs to be rounded to the nearest hundredth, all you'll do is, this fraction tells us to divide 36 divided by 70. So we do 36 divided by 70, and I get 0.51428, and that keeps going. But if we wanted to round to the nearest hundredth, we find the hundreds place, look one space to the right, that's 4 lower, so we would round this down. And so as a decimal, the probability that we get somebody who walked would be 0.51. So you'll be asked to write probabilities as fractions and as decimals. As a fraction, we're done here. We could reduce that, but we don't have to. As a decimal, do one more step, just divide. You'll get a decimal answer, and then make sure you round that however you're directed to. Okay, we've talked about the most important thing about probability. We've talked about dice, we've talked about cards, we've talked about tables. Now we get to one that sometimes does present a little bit of a challenge for students, and that's when we have sort of multiple events. A coin is flipped and a 6-sided die is rolled. So I'm going to do 2 different things here. I'm not rolling 2 dice. Instead, I'm going to flip a coin and roll a die. And I'm asked to find the probability of getting heads and an odd number. Okay, we've got to make sure we're clear about what and means. And you know, when a coin is flipped, there are 2 possible outcomes. And when a die is rolled, there are 6 possible outcomes. So if I multiply these together, fundamental principle of counting from last time we met, I'm going to have 12 total outcomes. You know, that's not that big a number. So I think what I'm going to do here is write down my sample space. We had a picture of the dice for a sample space. We had a picture of the deck of cards for a sample space. It's nice when we have a sample space to look at. So let's go ahead and see what this sample space would look like. So a coin is flipped. That's either going to be heads or tails. And a 6-sided die is rolled. That's going to be 1, 2, 3, 4, 5, 6. So I want to put together everything that could possibly happen, and you tell me if it doesn't make sense. But I could get a heads on the coin and a 1 on the die. I could get heads and a 2, heads and a 3, heads and a 4, heads and a 5, heads and a 6. I could get tails and a 1, tails and a 2, tails and a 3, tails and a 4, tails and a 5, tails and a 6. I knew I was going to have 12 outcomes, and I've got all 12 right here. So there is my sample space. I've got it. I can see a picture of everything that could possibly happen, and now I'm going to go answer this question that is, if I do this activity, what is the probability of getting heads and an odd number? And means both things have to happen. I have to get heads and I have to get an odd number. Well, probability of successes over outcomes, and I know there are 12 outcomes. So my denominator is going to be 12. Now I just have to find my successes. Okay, heads and an odd number. Well, it has to be heads, so I can throw all these out right away because they don't have heads. Heads and an odd number. Okay, well, that's heads and an odd number. That's got heads, but it doesn't have an odd number, so it's no good. That's got heads and an odd number. Heads doesn't have an odd. Heads and an odd number. Yep. Heads doesn't have an odd. So out of the 12 different things that could possibly happen, these 3 have heads and an odd number. So I have 3 successes, 12 outcomes. So the probability is 3 out of 12. Are there any questions about that before I have you try one that's very similar? Excellent. Okay, here goes. A coin is flipped and a six-sided die is rolled. So here again, right away, we know there's two things that can happen. There's six things that can happen. So I have 12 outcomes. This time it says, what's the probability of getting tails or an odd number? I'm going to set up a poll for this one and let you try it. Be patient and careful as you do this one. Have that sample space written down and then answer the question, keeping in mind that probability is successes over outcomes. This is probably the toughest poll question we have today, but all the ideas are the same. We can find our sample space. We can see how many outcomes there are. We have to identify those successes correctly. And once we have the number of outcomes and the number of successes, we can write our probability. Also, keep in mind the word or and what that means here. We'll go another 30 seconds and then we'll talk about it. You let me know if you have any questions about this one or if you need more time. All right, let's see where we are on this one. Okay, split just a little bit of a lead in one direction. So let's take a look at this one together. So the first thing I'm going to do is write down that sample space. We could get heads with a 1, heads with a 2, heads and 3, heads and 4, heads and 5, heads and 6, tails and 1, tails and 2, tails and 3, tails and 4, tails and 5, tails and 6. So that's our sample space. That's everything that could possibly happen. We'll eventually get to a place where we're not writing down the entire sample space, but when there's only 12 outcomes, it can be a lot easier to identify our successes when we just write the whole thing down. Now, we know there's 12 outcomes. So we know probability is successes over outcomes. So we know we're going to have 12 in the denominator. Now it's a matter of identifying those successes, keeping in mind what or means. What or means is I need at least one of these things to happen to have a success. So what that means is if I have tails, I have a success. Or if I have an odd number, I have a success. And if it happens to be tails along with an odd number, that's totally fine. That's still good because I need at least one of these things. As long as one of these things happens, it's a success. If it's tails, it's also an odd number, that's just fine. I just need at least one. So all these tails are going to be successes because they have tails in them. And then over here, let's see, that's heads and an odd. Well, odd number. Odd number is good enough. I'll keep it. Heads and an even. Yeah, that's no good. Heads and an odd. The heads doesn't work, but the odd does. Good enough. Heads and an even, no good. Heads and an odd number, that's good enough for me to count it. Basically, or is very open. Hey, if you're in tails, we're going to count you. If you're an odd number, we're going to count you. Heads and an even, no good. And so what I end up with here is, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 successes out of 12 outcomes. So the probability of getting tails or an odd number is 9 out of 12. Let me know if you have any questions on that one before we go forward into one more idea for today. Okay, very good, very good. Last thing we'll talk about today is the topic of odds. Odds are written as a ratio with a colon between the numbers. We are not going to write odds as a fraction. I've seen books out there that write odds as a fraction, and I don't love it. And here's the reason. For us, we're going to write probabilities as a fraction. We are never going to write odds as a fraction. And the advantage there is we're not going to mix them up. We're not going to get confused by looking at a fraction and going, well, is that odds or is that probability? We're not going to do that because we're never going to write odds as a fraction. Odds will be written as a ratio with a colon between the two numbers. An example might be like 15 to 1. That would be how we're going to write odds, not as a fraction, as a ratio of two numbers with a colon between them. The type of odds we're going to talk about are odds against. And the odds against some event are written as how many failures are there to how many successes are there. So odds against are written as failures to successes. Really easy to find the odds if we already know the probability. So that's the kind of thing we're going to take a look at. But odds against are always written as failures to successes. It's easy to remember which one of these comes first because odds against is kind of a negative word and failures is what goes first. So that's how it's easy to remember that odds against are failures to successes. Take a look at odds related problems. The probability of an event is 14 out of 19. Find the odds against this event. So I'm being asked for odds against. So what I need to write is failures to successes. I'm going to write that out. Failures to successes. Well, I've been given the probability, and the one thing that I know today, more than anything else about today, is that probability is successes over outcomes. So if I've been given that the probability of an event is 14 out of 19, then right away I know that the number of successes is 14. So I need to write failures to successes. I know there are 14 successes, so I'm halfway done writing the odds already. Now I got to figure out how many failures there are. And so as I look at this and I say, well, the number of outcomes, that's everything that could possibly happen. There are 19 things that could possibly happen. 14 of those are successes. So the rest of them are the failures. And so what we're going to do is we're just going to subtract. There's 19 things that can happen, subtract 14 successes, and find out that there must be 5 failures. And so when I want to write the odds against this event, there are 5 failures and 14 successes. So the odds against this event are 5 to 14. Please take note that probability is a fraction. Odds are not a fraction. We're never going to write odds with a fraction. Are there any questions on that before I have you try one? All right, here goes. The probability of an event is 4/13. Find the odds against this event. So find the odds against this event. You'll notice that none of those choices are a fraction because we're never going to write odds as a fraction. We've been given the probability, that's a fraction, and we will write probabilities as fractions, sometimes as decimals. We'll go another 30 seconds on this, and then we'll talk about it. Let's see how we're doing on this one. Unanimous. Very good. Odds is another one that I expect to go really well, so I'm really happy that it did. So we've been given that the probability is 4/13. So we know that 14ths is successes over outcomes. And we're looking for the odds against the event, so we need to write failures to successes. I can see right away, just looking at the problem, that the number of successes is 4, so I know that much. Now I just need to figure out that one other number, and if there's the number of outcomes is 13, so all the things that can happen, there's 13 of them. 4 of them are successes, so all the rest have to be failures. So I'll just subtract those 4 successes off, find out that I have 9 failures. And so failures to successes, the odds against the event is 9-4. Let me know if you have questions on that. We have another one we're going to do where we go the other direction, where we've been given the odds and we have to find the probability. That's what's next. Okay. The odds against an event are 5-7. What is the probability of this event? So now we're going the other direction. We've been given the odds and we have to find the probability. Really easy to tell it's odds because that's how we write odds. 5-7, and that's failures to successes. So I know when I'm looking for probabilities that I'm looking for successes over outcomes. And I'm told up here that the number of successes is 7. So this time I get the numerator right away, and I have to figure out what the denominator is going to be. What I can see from what I've been given is that there are 5 failures and 7 successes. I need to know the total number of things that could possibly happen. So now I need to add those together. There's 5 failures plus 7 successes means there's 12 total outcomes. So the probability of this event must be 7/12. If there are 5 failures and 7 successes, that means there's 12 total outcomes. If I know the number of successes and I know the number of outcomes, I can write that down as the probability. In this case, that's 7/12. All right, does anybody have questions about sample space, theoretical and experimental probability, dice questions, card questions, table questions, roll a dice and flip a coin, multiple event questions, and then odds. A whole bunch of different things, but they're really focused around Probability of successes over outcomes. That is the single most important thing. All right, just a couple more things I want to say before we finish our discussion of section 4.3. You may see a problem in your homework that uses the terms without replacement. If we're drawing a card from a deck or a ball from an urn and we're doing it without replacement, what that means is once that item's been taken out, we leave it out and we can't draw it again. This will be more important for us next week, but I think it may come up in one or two of the problems that are in the book for this section. So I want to mention it. If you see without replacement, it just means that once it's out, and it can't be picked again. And then something that may come up is you may see some new situations. We covered a bunch today in class, but you may come across something that's new and different. That's kind of on purpose. What that's about is forcing you to think about the most important thing about probability is anytime you're doing a probability question, what you're looking for is successes over outcomes. So if you see something that's a new situation and you're not exactly sure what to do, that's okay. You're looking for successes over outcomes. That's what we're after there.